At this point, you're familiar with Newton's third law. For every force, there's an equal and opposite reactive force. If you push on a wall, the wall pushes back on you, and the harder you push, the harder the wall pushes back on you. If you punch a boxing bag, the bag returns a force to your fist. The harder you punch it, the harder it forces back in your fist and the more it hurts. So, the general idea that for every force there's a reactive force is quite believable. The part that people quite often have difficulty believing is that the reactive force is truly equal to the original force. For example, consider a mosquito hitting the windshield of your car as the car is flying down the highway. What are the forces? Let's compare the force on each. Do we really believe Newton's third law? For every force, how can there be an equal and opposite reaction force? In order to tackle this, I'm going to tell some stories about a variety of car crashes, as students seem to visualize these stories best. I suppose we have so much experience riding in cars and seeing so many car crashes on TV and such that we just find this easy to visualize. Regretfully, my stories include some crashes with different animals. Take advantage of your ability to visualize these crashes and feel comfortable in that no people or animals were harmed in the making of this tutorial. You're just visualizing situations and getting smarter. First, let's visualize our car crashing into a similar car that was sitting still on the highway. If our car was traveling 100 kilometers per hour before the crash, and the cars moved together after the crash, let's picture some results. If the cars had equal and opposite forces on them, then F equals ma for each. Remember Newton's second law. Now, these two cars have the same mass, which tells us that for the forces to be the same, they also have the same change in motion, or acceleration. The combined cars would move off at 50 kilometers per hour. So, the first car has a change in motion. It went from 100 kilometers per hour going down the highway to suddenly 50 kilometers per hour. A drop of 50 kilometers per hour. The second car was sitting still, so its change in motion was that it went from 0 kilometers per hour to 50 kilometers per hour, an increase of 50 kilometers per hour. So they both had the same mass, and they both had the same change in motion or acceleration, so believing that they both applied equal and opposite forces on each other is pretty easy. Next, let's visualize our car crashing into a deer that was standing on the highway. In this case, there's a big difference in mass. The car is 1,000 kilograms, while the deer is 100 kilograms, or the deer is 1/10 the mass of the car. Following the crash, the combined car and deer would be moving at 90 kilometers per hour. So let's consider the changes in motion. The car's motion changed from 100 kilometers per hour to 90 kilometers per hour, a drop of 10 kilometers per hour. If you were riding in that car, the change in motion, that is a quick drop of 10 kilometers per hour, would definitely be felt. You'd better be wearing a seatbelt or you might be bashing your face on the dash. It's not as big an acceleration as hitting another car, but it's definitely going to be felt. The deer, on the other hand, got it worse. It went from going 0 kilometers per hour, or standing on the highway, to suddenly going 90 kilometers per hour. Thus, the deer experienced the same size of force, but the resulting acceleration was much bigger than the car. The same force for both the car and the deer in opposite directions. The mass of the car was bigger, so the change in motion or acceleration was smaller. Same force, but since the deer had a smaller mass, it had a much bigger change in motion. 1/10 the mass, 10 times the acceleration. Next, let's visualize our car crashing into a crow that was on the highway. The crow was busy picking things off the highway and didn't get out of the way in time. In this case, there was even a bigger difference in mass. The car is 1,000 kilograms as before, but the crow is only 1 kilogram. Or, the car is 1,000 times as massive as the crow. Following the crash, the combined car and crow would be moving at 99.9 kilometers per hour. So let's consider the changes in motion for each. The car's change in motion, it went from 100 kilometers per hour to 99.9 kilometers per hour, a drop of 0.1 kilometers per hour. If you were riding in the car, this change in motion, that is a quick drop of 0.1 kilometers per hour, would be felt as a minor bump. You'd know you hit something, and you might feel the change in motion as your head might move ahead slightly, but it's not likely to cause a dangerous situation for you in the car. The crow, on the other hand, got it much worse. It went from going 0 kilometers per hour, standing on the highway or just taking off, to 99.9 kilometers per hour, all quickly. This is a huge acceleration, and the crow will not survive the collision. The crow experienced the same force in the opposite direction, but the resulting acceleration was much bigger than the car's acceleration. Exact same force for both the car and the crow in opposite directions. The mass of the car was much bigger, so the change in motion for the car, or its acceleration, was much smaller. Same force, but since the crow had a smaller mass, it had a much bigger change in motion. 1,000th the mass, 1,000 times the acceleration. So, we're back to the car hitting the mosquito. Hopefully, you're reconsidering your original thoughts. It's true that the mosquito and the car experience equal and opposite forces. The resulting acceleration or change in motion for each was different. The car has about 1 billion times the mass of the mosquito. So, since the force on each is the same, and the mass of the car is 1 billion times bigger, then the acceleration or change in motion would be about 1 billion times smaller. Following the crash, the combined car and mosquito would be now moving at about 99.9999999 kilometers per hour. The car's motion essentially hasn't changed. You didn't feel the change. It was too small to notice. The mosquito, on the other hand, got it much, much worse. It went from going 0 kilometers per hour to going essentially 100 kilometers per hour. This is a crazy big acceleration, and we have one less mosquito on our planet. In this tutorial, we took a closer look at Newton's third law. For every force, there's an equal and opposite reaction force. We looked at the situation where a really big object collided with a really small object, car and mosquito for instance, and realized that most people can get tripped up with this situation. I mean, look at the car, look at the mosquito. How can they be equal forces? But if you take your understanding of Newton's second law and combine it with some smart analysis, we can make total sense of the fact that the forces are, in fact, equal. It's not a difference in forces that makes the collision much worse for the mosquito. It's the sudden change in motion, or acceleration, that makes the collision deadly for the mosquito and not even noticeable for the car. The difference in mass between the two objects means that the same force will cause dramatically different accelerations. The mosquito's experience is a huge acceleration, causing its demise, while the car, because of its huge mass, experiences a much smaller change in motion. Same force, different results.